So yeah, I'm also going to talk about rational MPC. It will be a bit more of a traditional take on it, I guess. But let's see. Well, we all know traditional MPC, where we have multiple parties, everyone gets some input, they exchange some messages, and eventually they will produce some outputs, which hopefully is the evaluation of some function. Then usually the security model is, which we've already heard, we have some corrupted parties in this, and then we prove something like the corrupted parties can't actually learn anything about the honest parties' inputs, and the corrupted parties cannot influence the computation other than by choosing their output, or potentially by aborting. Well, we know this definition, and I would posit basically to motivate the rational part of it. I would posit the following criticism on this definition, which is, in a way, this definition is very strong, which we just heard, because it does protect against completely irrational attacks. So if I have an adversary, like a corrupted party, it can behave completely stupidly, self-destructively, and we're basically covering all attacks, even if they are completely stupid to do for that party. It's also, in a sense, this standard definition is a bit too weak even, because it assumes that we have at least one party in this that just completely altruistically, self-sacrificingly just follows the protocol to the T. And rational MPC has essentially asked the question, okay, what if nobody in these protocols are actually completely honest, altruistically honest, and nobody's actually completely malicious? Instead, everyone is kind of rational and tries to maximize some sort of utility. Okay, let's get into this. So the more formal part of it is, if we are doing rational MPC, we need to define a game. And this game consists of n players, which are kind of the MPC participants. Each player chooses a strategy, SI. A strategy in the rational MPC setting is an interactive Turing machine that explains how you would behave during the protocol. Then the game starts, which means that the Turing machines get some randomly sampled input, where whatever the distribution of that input may be. Everyone gets some random input. We run all of the Turing machines. They interact with each other. I'm doing synchronous rounds, broadcast, everything like the easiest settings, because this is already complicated enough. And then eventually each Turing machine outputs some output yi. And then the goal for each player, intuitively and formally, is that each player tries to maximize the expected utility. So for the utility, we're looking at, can I do stuff like this? Yeah. For the utility, we're looking at what are all of the inputs and all of the outputs, and then this utility function tells us, like, how good is this outcome for party I? And what we're interested in is the expected, like, goodness for this for the player. Okay, and then our job as basically protocol designers is to come up with a mechanism. A mechanism is basically a prescription. I'm telling everyone, like, okay, this is the Turing machine that you should choose as a strategy, and if you do that, then everything should be fine. The intuitive security expectations that we have for all of this will be something like it should be rational to actually follow this prescription, meaning that for player I, it should be rational to play this strategy SI. So I could have such a protocol here, would be an example for a mechanism. I'm not going to go into details. Now, if I'm saying, like, it should be rational to follow this prescription, what do I mean by that? The standard notion for this is kind of Nash equilibria, which I guess most people are mostly familiar with, where the idea is that it doesn't help anyone to unilaterally deviate from the protocol. More formally, basically, I'm comparing two scenarios. I'm looking at all of the players and all of potential alternative strategies that the players could take. And then basically, if I'm deviating from playing my honest strategy to playing this other strategy, then my utility only decreases. So I can't gain anything from deviating. There's a little bit of a lie, because in the computational setting, I can potentially gain something by deviating a little bit. So in the computational setting, we're saying you can't gain non-negligibly by deviating. This is kind of a necessary condition because you can always, like if there's, let's say there's public key encryption involved, what I can always do is just guess the secret key or like add one round of guessing the secret key. And this kind of increases my utility a little bit, but not by a lot. Okay, so basically before I look at examples, let's actually talk about how to build rational MPC protocols in the more traditional blueprint for it, I guess. Basically, if I want to do arbitrary MPC computation in a rationally secure way, the idea for this is that everyone gets the input at the start. Then, as a first step, we need to make sure that this function that we're computing is actually kind of rationally compatible in the sense that it doesn't make sense for the parties to just lie about the input because they can always do this. There's nothing we can do about that. But if we have such a function where it doesn't make sense to lie about your input, let's say we have like a second price auction or something, then we can run a protocol that kind of works like this. We're doing GMW-style maliciously secure MPC at the start. So everyone commits to their inputs. We do some secret sharing of all of the inputs. We do zero-knowledge proofs. We do round by round. Everyone gets their shares updated. And then at the end of this, everyone holds a share of the function value. And basically, this part is, rationally speaking, somewhat easy to handle because there's not a lot of deviation you can do in GMW. You need to prove that you've done everything exactly correctly. So there's not a lot. Yeah, basically, if you try to deviate from this protocol, you will just be ejected from the protocol. And so deviation doesn't make sense there. What is interesting and what we will talk about mostly today, or in this talk, is the last step, where after everyone gets the shares of the result, we have some secret reconstruction protocol where everyone actually learns the result, the non-secret shared result. And this will turn out to be kind of the crucial part of rational MPC in the flavor that I'm presenting here. Okay, so secret reconstruction seems to be kind of the building block. So let's take a look at what this is. It's actually also just a standard MPC, so the scenario is exactly the same. We have players choosing Turing machines as strategies. Then we start the game. The input for the game is now the secret shared secret. So we choose the input is kind of a randomly chosen secret. And then everyone gets as input basically a share for that secret and a signature on that share. Basically to make our lives easier. Then after everyone gets the input, we run the Turing machines that the players chose. Everyone outputs something, and then the utility will be, we have some light assumptions on the utility, which is that probably players prefer to output the correct value, the correct secret, over outputting the wild secret, which seems natural. And the other one is potentially players prefer others not to output the correct secret. So ideally, if everything goes very well for player I, then player I learns the correct secret. Nobody else learns the secret at all. Okay, so these are the utilities. So let's get a little bit of a feeling of what this looks like. I'm giving you a very simple protocol where we do the secret reconstruction, which is, it's very simple. So we do n-1 out of n secret sharing. So you need n-1 shares to reconstruct. And then the protocol that I'm proposing here, which I didn't come up with it, but the protocol is just everyone just takes their share, broadcasts it to everyone else. Then everyone receives those shares, checks the signatures, and if you get enough shares, you just reconstruct the secret. It's kind of the easiest thing you can do.
Okay.
So let's take a look at whether this is Nash equilibrium. It turns out to be in Nash equilibrium to everyone to just play these kinds of protocols. Why is that? Well, we can take a look at basically this player and ask ourselves, does it make sense for this player to deviate or what? If the player plays the protocol honestly, then everyone learns the secret. So honestly means that I just broadcast my shares and the signatures. Everyone learns the secret. This is kind of a good outcome, or an okay outcome. If I try to deviate from this, so I could try to send the wrong share or not send any share at all. Actually, this doesn't change anything for anyone because the n-1 other parties will still broadcast their shares. They still have enough shares to reconstruct their secret. So everyone will still output the correct secret. Essentially, because this is n-1 out of n secret sharing, doesn't really matter whether I actually participate or whether I do something weird. I also can't really cheat by sending a wrong share because all of the shares are signed. So whenever I try to send a wrong share, someone will detect it. A more interesting case potentially is looking at n out of n secret sharing, where if we look at the same protocol where everyone just broadcasts their shares, this actually turns out to not to be a Nash equilibrium for the following like very foundational issue that we're running into this a lot, which is if this party follows the protocol, then everyone learns the secret. If the party decides not to broadcast anything, then this is actually better for this party because now everyone else doesn't learn anything. They are just missing the share of that party because I'm not giving it to them. But this party still does learn the share because it still gets all of the shares from the others because the others are still following the protocol. So this is kind of, like one of the foundational issues for this, that one good strategy in these secret reconstructions often turns out to be just not to broadcast your shares, to deny broadcasting the shares. Okay, so that's kind of unfortunate because what we would like to do is secret reconstruction even for n equals 2, but we can only do it for n-1 out of n secret sharing. So for n equals 2, that's not really interesting. That's 1 out of 2 secret sharing. So it would be cool to make it n out of n work after all. And there actually turns out to be a protocol that does exactly that, which I don't really have time to get into. But basically the idea is that I can manage this weird strategy of not broadcasting my share and still learning the shares of everyone else by hiding in which round I'm actually supposed to broadcast my share. So what's happening in this protocol is essentially I'm doing multiple rounds of broadcasting, and the deviator doesn't know whether when they broadcast their share here, whether this is kind of a dummy share or whether it's the share of the actual secret. So in this way, I can kind of punish people trying to not broadcast their share by saying, okay, if you don't broadcast your share, you will be punished by being removed from the protocol, and potentially you didn't even learn the secret. If it was like a dummy round, you didn't learn anything. So this is a very elegant protocol where you can actually make n out of n secret sharing work. But don't really have time to get into this. But yeah, you can set the parameters for this to make sense. To get into what I actually want to talk about, so all of this was basically a bit of flavor to make you understand what we are thinking about in rational MPC. What we were interested in the paper that I'm presenting is actually weakly dominated strategies, which has some interesting story behind it. Let's first talk about what weakly dominated strategies are. Basically, we had Nash equilibria, answering the question whether some strategy profile is rational to play for players. This will be similar in that we also have some criterion that tells us whether a certain strategy is rational or not. For weak domination, this works as follows. We say that a strategy as better weakly dominates some other strategy named as bad if the better strategy is sometimes better. So there exists some strategy profile of the other parties where if I'm switching to the better strategy, I'm actually profiting. So this is good for me. So there's some weird scenario where I'm actually improving by switching to as better. And actually, as better is never worse than as bad, meaning that whatever the other parties do, what the other players are doing, the utility of my as better is actually always larger than the utility of as bad. So what does this mean? In the computational setting, of course, we need to do it's sometimes noticeably better, and it's never more than negligibly worse. So the idea for this kind of criterion is if I'm telling you to play as bad, and there is a strategy as better, which just guards you against some weird behavior. So it's sometimes better, in some weird scenarios better, and it's never worse for you to play as better. Why shouldn't you switch to as better? Right? It's just kind of it's just the better strategy. So this gives us an additional criterion next to Nash equilibria to talk about whether a strategy is kind of rational to play. We spent some time trying to find what is the spirit of this definition, what does it actually give us? And I think one good example for this is this protocol over here, where let's do n-1 out of n secret sharing. This was the simple case, right, where we could just broadcast the shares. And now I'm telling you should play this protocol that's rational to play. The protocol that I'm telling you to play is you do nothing in the first round. Then you wait after the first round and check whether everyone told you to self-destruct. If they do, then you self-destruct. You output the worst secret and you stop participating. If they don't, then you proceed with a proper protocol for secret reconstruction. So basically, if we just look at this as rational humans, we should notice that the red step is completely stupid to play. So I should never do this. I should always remove the second step. And if people tell me to self-destruct, I just shouldn't do it. That's kind of obvious. Still, the Nash equilibrium actually has no issue with this strategy at all. Because for the Nash equilibrium, we're just looking at what if everyone plays the strategy and just one party thinks about deviating. If everyone plays the strategy and everyone does nothing in round one, then the second case never happens, right? So nobody's actually telling me to self-destruct in the Nash equilibrium case. So in this sense, it doesn't really matter whether or not I have the self-destruct condition in there or not. However, weak domination would correctly identify that this is a stupid strategy to play, because weak domination would say, okay, if I'm removing this condition here, the self-destruct, then this is sometimes better for me in the case that other people actually tell me to self-destruct. And it's actually never worse for me because, there's nothing worse than self-destructing. So this kind of gives you a flavor, an example for what weak domination should give you rationally. Weak domination has sort of interesting history, just very briefly. In 2004, people identified it as an interesting property to have for protocols. So protocols should survive this weak domination. They shouldn't be weakly dominated. And then they came up with protocols that claim to achieve that. Then in 2006, they came up with even better protocols for that, which is kind of this hiding the last round protocol that I briefly showed you. Then in 2008, Colin Naor essentially said that this weak domination idea has some weird weaknesses in the sense that essentially you can take the stupidest strategy ever and it would still not be weakly dominated in some restricted model. They proved this and essentially said, okay, whatever we did here seems to, it's nice that we can prove that stuff is not weakly dominated, but nothing is really weakly dominated, so it's not really that interesting. We looked at it quite some time later and basically saw that actually what seems to be the case if we kind of remove this restricted model here, that actually it's not the case that nothing is weakly dominated, so it's not a very weak property. Actually, it seems to be the case that everything is weakly dominated, so it's a over-eager property. It's basically destroying every chance of ever coming up with a rational MPC protocol. So that's basically the result that we mostly have. I will briefly go over this idea because the counterexample is pretty simple. So what I'm claiming is that no mechanism, no matter what you tell me to play, none of this will survive weak domination in the sense that I can always come up with kind of a better strategy for you to play that weakly dominates your strategy. So we start with some arbitrary mechanism, can be a very beautiful protocol with resharing and broadcasting and everything. we don't really care what it does. What I'm basically claiming is this party here should actually play the following alternative strategy. This following alternative strategy is that we behave exactly like the original strategy, but I'm adding one check into the protocol. The check is that if in the first round, everyone happens to lose their mind and just sends me or just leaks me their input in plain, then I would just take this leakage, reconstruct the signature, check the signatures, reconstruct the secret, and I'll just eventually output the correct secret. If people don't do this, then, I will follow the protocol as usual. Okay, so it's just really this one additional check here. If everyone loses their mind, then I can actually output the correct secret. So why is this weakly dominating the original strategy? So first of all, this is sometimes better. This is kind of easy to see. It's better in the case where everyone does lose their mind and plays the strategy where they just leak their input to me and then just stop. Now, this is a strategy we can look at. And in this case, actually, this new strategy will output the correct secret. And the old strategy would probably mostly freak out because the first message was not in the format that they expected. So it may not output anything. There's a more elegant argument, but for now, let's assume that this is the case. It's also never worse than the original strategy, because no matter what the other parties are doing, the only way that I might ever deviate is by outputting the correct secret, which the signatures will basically guarantee me that whenever I do deviate, the secret that I'm outputting, that I'm reconstructing, needs to be the correct one, because otherwise someone forged the signature. So yeah, the strategy is also never worse. So overall, this new strategy weakly dominates basically any reasonable strategy that you can come up with. Now, what you might say is, wait, actually, I could easily fix this by adding this weird check into my original protocol. Because then, if I add this, basically, if I'm adding this check again, it wouldn't do anything anymore. The original protocol already does this check. Or maybe the protocol doesn't freak out in the first round if everyone sends this leak message, but actually does something reasonable. So what I'm arguing there is actually I can generalize this counterexample in various ways, where maybe I'm just not looking at this leak message like this, but I'm looking at everyone sending me their shares in some weird encoding. So for example, I'm hoping for everyone to send me their shares encoded in base 64, or, with inverted bits, or whatever weird encoding you can come up with. And essentially, unless your protocol lists every possible encoding, which is not possible, one of these encodings will actually improve my chances against weird strategies without harming my utility. So long story short, what does this mean? Basically, every protocol that we can imagine that has authenticated shares, which is all of them pretty much, is weakly dominated, which means that in some sense, it's kind of irrational to play if you want to look at it like this. And then the counterexample is rather simple. Also means that most of the nice protocols that do have some nice properties for Nash equilibria, which claim to also be secure against weak domination, actually are not secure. Okay, so takeaways. We talked about rational MPC, which is sometimes a nicer model for MPC, especially in scenarios where we don't have altruistic parties. And everyone is kind of just trying to behave rationally. We saw that weak domination is way too strict. It's kind of an interesting notion. And it's kind of one of the, we long believed it to be too weak. And now we kind of know that it's actually way too strong, which I don't know. So it was broken before. It's still broken now, but kind of differently broken. We've shown that no known protocol survives weak domination. And also we basically generalize this and show that there can't be, in certain scenarios, there can't be any protocol that survives it. There's a lot of work to be done in this, in this field, I would say. It would be cool to find a replacement for weak domination. There are a bunch of alternative definitions where potentially you can replace weak domination with. However, I've shown you this self-destruct example, and we haven't seen any definition that actually which intuitively should be removed from the pool of rational strategies, but we haven't seen any definition that actually rules it out, other than weak domination, but weak domination rules out everything, so, doesn't really give us much. And the other direction might be to actually look for better protocols or better settings where this counterexample or this impossibility doesn't really hold. Yeah, that's it. Thanks.